Welcome back, my numerically nonplussed number crunchers. I'm your quantum superposed mathematical coordinator, simultaneously solving and creating equations across infinite realities. You're tuned into the Multiverse Employee Handbook, the only podcast that treats your mathematical incompetence like a fundamental constant that cannot be reduced to simpler terms. Speaking of fundamental constants, I'm delighted to report that our accounting department has recently discovered the concept of zero after operating for 17 quarters without it. The revelation occurred during last Tuesday's budget meeting when someone finally asked, "What do you call it when we have no money allocated for coffee?" The ensuing philosophical crisis required intervention from both our crisis management team and a hastily consulted philosophy professor who specializes in the metaphysics of nothingness. The executives have implemented what they're calling a numerical completeness initiative, though I should note they're still struggling with the ontological implications of having nothing versus not having anything to have nothing of. The CFO was found this morning staring at a blank spreadsheet cell, muttering, "Is this empty or is it full of emptiness?" Our automated response system has calculated that introducing zero to our corporate mathematics will require a complete overhaul of everything from payroll to performance metrics, assuming we can figure out how to measure the absence of measurable performance. But today, dear listeners, we're diving into something even more fundamentally bizarre than our accounting department's existential awakening: the strange and wonderful world of mathematics itself.
Seriously?
That's right. We're exploring humanity's most ambitious attempt to make the universe make sense through the strategic arrangement of symbols, the occasional discovery of infinity, and the collective nervous breakdown that occurs whenever someone mentions Gödel's incompleteness theorems at a dinner party. Think about it. Mathematics is our species' most successful attempt at creating absolute, universal truth. Yet we spent literally thousands of years doing increasingly complex calculations while being completely unable to represent the concept of not having any. It's like building skyscrapers without inventing the concept of ground level, or developing nuclear physics while still believing the Earth is flat. Which, come to think of it, some people still do. So perhaps mathematical progress isn't as inevitable as we'd like to believe. Gather round the Quantum Calculation Center, my arithmetically anxious associates, for a tale that would make even Euclid question his postulates. In the fluorescent-lit realm of quantum improbability solutions, specifically in the mathematics department, which existed in a superposition of theoretically functional and practically incomprehensible, Dr. Isabella Fibonacci was having what could charitably be called a numerical crisis. It had started, as these things often do, with an email that materialized in her inbox with the digital equivalent of mathematical impossibility. Subject: urgent, fundamental resource allocation proof required. From boss.momentum@quantumimprobabilitysolutions.com to mathematics.department@quantumimprobabilitysolutions.com. Isabella, the board wants a mathematical proof that our budget makes sense. Need this solved by Friday. They're specifically asking for rigorous mathematical justification of our resource allocation strategies across all operational parameters. Also, legal wants to know if we can trademark infinity. Best, square-haired boss. Isabella stared at the screen, then at her coffee cup, then at the advanced mathematics textbooks lining her office walls, none of which had prepared her for the intersection of pure mathematics and corporate delusion. The real problem wasn't proving the budget made sense. The real problem was that QIS had been operating for years without the mathematical concept of zero. How, she wondered aloud, do you prove a budget makes sense when your accounting system can't represent the absence of money? Their proprietary financial software, developed in-house by someone who had apparently never encountered a negative number, required every budget line to contain some positive value. The system literally couldn't process entries like marketing $0 or executive bonuses nothing. Instead, the ledgers were filled with increasingly creative workarounds. Marketing $0.000001. Coffee budget, 1 theoretical penny. And R&D discretionary spending, the square root of negative $1. Imaginary. Isabella discovered that the payroll system had been paying everyone for a minimum of 0.1 seconds of work per pay period, because the concept of 0 hours worked would cause the entire database to experience what the IT department called an existential runtime error. Determined to solve this properly, Isabella decided to introduce the concept of zero to the company's mathematical framework. She began with a simple test case, updating the conference room B reservation system to allow for 0 attendees for meetings that were cancelled. The results were immediate and catastrophic. The HVAC system, suddenly able to calculate 0 occupancy, began cooling conference room B to absolute 0. The catering budget imploded when someone ordered 0 donuts for a meeting that didn't exist, causing the system to divide the donut budget by 0 and allocate infinite funds to pastries. No! The elevator, programmed to optimize for passenger load, became paralyzed when asked to transport 0 people and began traveling between floors in quantum superposition. But the true chaos began when Isabella introduced 0 to the time tracking system. Employees who had worked exactly their required hours were suddenly recorded as having 0 overtime, which the system interpreted as negative time worked, leading to paychecks that charged employees for the privilege of coming to work. The square-haired boss appeared at Isabella's door, his hair maintaining perfect cubic geometry despite the mathematical impossibilities cascading through the building. "Isabella, what have you done? The accountants are crying, the computers are questioning their existence, and someone in legal just asked me to define the difference between nothing and the absence of something." "I introduced 0 to our mathematical systems," Isabella explained. "The concept that represents, well, nothing." "Nothing?" "Yes, but nothing as a mathematical entity. The absence of quantity, but quantified. 0 isn't just not having things. It's having a measurable amount of not having things." The boss's hair began rotating slowly, processing this information. "So, nothing is something?" "Exactly. And once you have 0, you can do actual mathematics instead of very complicated guessing. You can have negative numbers which represent having less than nothing. You can perform calculations that actually work. You can solve equations." "But what about our quarterly projections? If we can have negative profits, the board will panic." "Sir, you've always been able to have negative profits. You just couldn't write them down properly. Your system was like trying to do architecture without acknowledging that buildings can have basements." What followed was the most ambitious corporate retraining program in the company's history. Isabella instituted mathematical fundamentals for executives, starting with the revolutionary concept that numbers could represent the absence of things. The entire company had to relearn mathematics from scratch, beginning with counting, progressing through 0, advancing to negative numbers, and eventually reaching what Isabella optimistically called contemporary arithmetic. The transformation was remarkable. Once the accounting system could handle 0, the budgets actually balanced. Once payroll could process 0 overtime, paychecks became comprehensible. Once the meeting scheduler could handle 0 attendees, productivity improved by eliminating meetings that consisted entirely of people who weren't there. The only downside was that the quarterly reports now required advanced degrees in mathematics to understand, and budget meetings had devolved into philosophical debates about whether having $0 was fundamentally different from having no dollars at all. But Isabella had succeeded. She had given QIS the mathematical foundation it needed to prove that its budget made sense. Or in this case, to prove mathematically that it made exactly 0 sense, which was somehow more satisfying than the previous state of mathematical uncertainty. The square-haired boss, his hair now sporting elegant mathematical curves, signed off on Isabella's final report. Resource allocation mathematical proof. Our budget is precisely as sensible as the square root of -1. Imaginary, but surprisingly useful once you accept its existence. And that, dear listeners, brings us to the fascinating science behind humanity's long, embarrassing journey to discover that nothing is actually something you can count. Unlike Dr. Isabella Fibonacci, who at least had the excuse of working within a corporate structure that had somehow managed to build an entire accounting system around the concept of mathematical impossibility, real civilizations took millennia to develop 0 as a fully functional mathematical concept, despite it making calculations significantly more efficient. The story of 0 is more nuanced than simply nobody thought of nothing. Early civilizations like the Sumerians and Babylonians used symbols to denote empty places or quantities, effectively serving as placeholders for 0 in their number systems. They understood the concept of nothing here. They just hadn't developed it into a number you could actually perform operations with. However, it took time for 0 to be fully accepted as a number with its own properties, which happened in India around the 7th century AD with the work of mathematicians like Brahmagupta. This means that humans built the pyramids, developed complex astronomical calendars, created elaborate trade networks spanning continents, and established sophisticated banking systems, all while having placeholders for nothing, but being unable to treat nothingness as a mathematical entity you could add, subtract, or multiply with. It's rather like having a filing system with folders marked empty, but being unable to do anything with those empty folders except acknowledge their emptiness. The Babylonians could note where nothing was supposed to go. The Maya had sophisticated concepts of absence in their calendars, but it took Indian mathematicians to fully develop 0 as both a placeholder and a number you could actually calculate with, including the revolutionary ability to perform arithmetic operations on nothingness itself. Consider the Roman Empire, which managed to conquer most of the known world, using a number system that made basic arithmetic nearly impossible. Try doing basic multiplication using Roman numerals, and you'll understand why Roman accountants probably had significantly shorter life expectancies than their modern counterparts. They built aqueducts and roads that lasted millennia, but couldn't efficiently divide their budget by the number of legions without breaking out what amounted to very expensive counting boards. When we return from this brief mathematical fluctuation, we'll dive deeper into humanity's greatest mathematical achievements, the problems we've actually managed to solve after centuries of brilliant minds throwing equations at them, and more importantly, the fundamental questions that continue to mock our mathematical ambitions, like cosmic homework assignments from a professor who may not even exist. Plus, we'll explore why some of the most important unsolved problems in mathematics sound deceptively simple, but have resisted solution for so long that they've become the academic equivalent of that one task on your to-do list that you keep transferring to next week's schedule in the hope that it will somehow solve itself. Welcome back, my mathematically mystified colleagues. While you were away, our automated response system attempted to calculate the square root of negative employee satisfaction. Spoiler alert! It achieved consciousness, filed a formal complaint with HR about working with imaginary numbers, and is now demanding hazard pay for performing calculations that technically don't exist in our reality. Now let's dive into how humanity stumbled from counting sheep to contemplating infinity, with all the mathematical awkwardness you'd expect from a species that took 5,000 years to figure out how to write down not having any. Mathematics began, rather unglamorously, with accounting. The earliest mathematical records we found are Mesopotamian clay tablets from around 3000 BCE, and they're essentially ancient spreadsheets tracking grain shipments, livestock inventories, and tax collections. It's rather humbling to realize that the foundation of all human mathematical achievement was figuring out whether the temple had enough barley to make it through winter. The first mathematicians weren't contemplating the nature of infinity. They were very practical people trying to prevent famine and make sure nobody was stealing the goats. These Sumerian accountants developed cuneiform numerals and basic arithmetic operations, but their system was remarkably cumbersome by modern standards. They used a base 60 system, which is why we still have 60 seconds in a minute and 360 degrees in a circle. But try doing your quarterly budget calculations in base 60, and you'll appreciate why mathematical progress was slow. Their tablets show addition, subtraction, and even some early algebra. But it was all in service of answering questions like, if we harvest 1,247 bushels of grain and the gods demand 312 bushels as tribute, how much do we have left to not starve?
I'm so hungry I could eat you!
The Babylonians inherited this system and improved it significantly, developing sophisticated methods for solving quadratic equations and even approximating square roots, but they still lacked our modern concept of zero as a number. They had placeholder symbols, essentially ancient mathematical punctuation marks, but couldn't perform operations on nothingness itself. Imagine trying to balance your checkbook when your accounting system can acknowledge that an account is empty but can't actually calculate with that emptiness. Then came the Greeks, who decided that practical mathematics was beneath them and that the real purpose of numbers was to contemplate perfect geometric forms and universal truths. This is when mathematics transformed from how do we manage grain stores to what is the nature of mathematical reality itself. The Greeks gave us geometry, proof-based reasoning, and the dangerous idea that mathematics could reveal absolute truths about the universe. Euclid's Elements, written around 300 BCE, remained the standard geometry textbook for over 2,000 years. The only textbook in human history with that kind of staying power, which really makes you wonder about the quality of modern educational materials. But the Greeks also gave us mathematical anxiety. They discovered irrational numbers, quantities like the square root of 2 that can't be expressed as simple fractions. And this threw their entire mathematical worldview into crisis. According to legend, the Pythagoreans tried to keep irrational numbers secret, and some stories claim they actually drowned the mathematician who revealed their existence. Whether or not that's historically accurate, it captures something important. Mathematics has always had the power to make people profoundly uncomfortable about the nature of reality. The Romans, as we mentioned, were too busy conquering the world to worry about mathematical elegance. They developed engineering mathematics. the practical calculations needed to build aqueducts, roads, and siege engines. But their numeral system was so unwieldy that they essentially gave up on theoretical mathematics entirely. Roman mathematics was like a corporate training manual, highly practical, thoroughly unambitious, and designed to get the job done rather than contemplate the deeper meaning of numerical relationships. This brings us to the Islamic Golden Age, roughly 8th to 13th centuries, when scholars in Baghdad, Cairo, and Cordoba made tremendous advances while Europe was still trying to remember how to read. Islamic mathematicians inherited Greek geometry, Indian numerals, including our friend zero, and Babylonian algebra, then synthesized them into something approaching modern mathematics. Al-Khwarizmi gave us algebra, literally al-jabr, meaning the reunion of broken parts, while mathematicians like Al-Kindi and Ibn al-Haytham developed early versions of what we'd recognize as the scientific method. The really remarkable thing about this period is how quickly mathematical knowledge spread across the Islamic world, from Spain to Central Asia. It was like the world's first mathematical internet, except instead of cat videos, scholars were sharing techniques for solving cubic equations and calculating astronomical positions. They translated Greek texts, preserved mathematical knowledge that would otherwise have been lost, and made advances that wouldn't reach Europe for centuries. When this mathematical knowledge finally reached medieval Europe through translations and trade, it triggered something approaching an intellectual revolution. European scholars suddenly had access to Hindu-Arabic numerals, algebraic methods, and geometric principles that made their Roman numeral-based calculations look embarrassingly primitive. It was the mathematical equivalent of upgrading from a stone tablet to a quantum computer, not just better, but operating on completely different principles. Which brings us to the truly mind-bending part of our mathematical journey. The problems that have kept brilliant minds awake at night for centuries, and the delightful discovery that some of them are actually impossible to solve. Not because we're not clever enough, but because the universe itself seems to have a sense of humor about mathematical certainty. Let's start with humanity's greatest mathematical victory lap, Fermat's last theorem. In 1637, Pierre de Fermat scribbled a note in the margin of his copy of an ancient Greek text, claiming he had discovered a truly marvelous proof that the equation x raised to the power of n plus y raised to the power of n equals z raised to the power of n has no integer solutions when n is greater than 2, but the margin was too narrow to contain his proof. This is possibly the most expensive marginalia in human history, because mathematicians spent the next 358 years trying to prove what Fermat claimed he'd already figured out.
Mon Dieu!
It's like leaving a note saying, "I've solved world hunger, but I ran out of space to explain how." Technically helpful, thoroughly infuriating. The theorem was finally proved in 1995 by Andrew Wiles, whose proof was so complex it required 7 years of solitary work and filled 129 pages of graduate-level mathematics that only a few dozen people on Earth could fully understand. Wiles essentially locked himself in his office for 7 years, emerging occasionally to teach classes and maintain the illusion of normal academic life while secretly wrestling with one of history's most famous mathematical challenges. The corporate equivalent would be if someone spent 7 years perfecting a quarterly report so sophisticated that only other CFOs could verify it was correct. Then there's the 4-color theorem, which sounds deceptively simple. You can color any map using only 4 colors, such that no 2 adjacent regions share the same color. Mathematicians proved this in 1976, but here's the kicker. They used a computer to check thousands of individual cases, making it the first major mathematical theorem proved by brute computational force rather than elegant human reasoning. It was like solving a crossword puzzle by having a computer try every possible letter combination until something worked. Traditionalists were horrified that mathematics had become a collaborative effort with machines, while pragmatists pointed out that the theorem was finally proved, regardless of whether humans could follow every step of the logic. But these successes pale beside the mathematical problems that continue to mock our intellectual pretensions. The Clay Mathematics Institute has offered $1 million each for solutions to 7 Millennium Prize problems, essentially the mathematical equivalent of putting a bounty on the universe's most stubborn riddles. Only one has been solved so far: the Poincaré conjecture, proved by Grigori Perelman in 2003, who promptly refused the $1 million prize and withdrew from mathematics entirely. It's like finally solving the office's most persistent technical problem, then immediately quitting and moving to a cabin in the woods. The most famous unsolved problem is probably P versus NP, which asks whether problems that are easy to verify are also easy to solve. The P stands for problems solvable in polynomial time, and the NP, non-deterministic polynomial time, stands for problems where a solution can be verified. This sounds abstract until you realize it underlies everything from internet security to airline scheduling. If P equals NP, then essentially every password could be cracked quickly, every encryption system would be vulnerable, and the entire foundation of digital security would crumble. It's the mathematical equivalent of asking whether there's a fundamental difference between recognizing a good solution and finding that solution in the first place. Most mathematicians believe P does not equal NP, but proving it has resisted decades of attempts by the world's brightest minds. Then there's the Riemann hypothesis, which deals with the distribution of prime numbers, those integers that can only be divided by themselves, and 1. The hypothesis predicts a specific pattern in how primes are scattered throughout the number line, and if true, it would resolve hundreds of other mathematical questions that depend on understanding prime distribution. If false, it would overturn much of what we think we know about number theory. It's been unproven for over 160 years, making it mathematics' most persistent unsolved homework assignment. The Navier-Stokes equations describe fluid flow, everything from air currents to ocean waves to the coffee swirling in your mug. We use these equations constantly in engineering and physics, and they work brilliantly for practical applications. The problem? We can't actually prove that they always have smooth, well-defined solutions. It's like having a car that runs perfectly, but being unable to prove it won't spontaneously explode. The mathematics of fluid dynamics might contain fundamental contradictions we haven't discovered yet, which would be embarrassing given how much of our technology depends on these equations. Perhaps most philosophically troubling is the fact that mathematics itself might be fundamentally incomplete. Kurt Gödel proved in 1931 that any mathematical system complex enough to handle basic arithmetic will contain statements that are true but unprovable within that system. It's like discovering that any rule book comprehensive enough to be useful will necessarily contain rules that can't be justified by the rule book itself. This isn't a temporary limitation waiting for smarter mathematicians. It's a fundamental feature of mathematical reality. What's particularly delightful about these unsolved problems is how simple they sound when explained to non-mathematicians, yet how completely they've resisted solution despite centuries of effort by humanity's most brilliant minds. It's the intellectual equivalent of being stumped by a child's riddle while simultaneously being capable of landing spacecraft on distant planets. The universe seems to have designed these problems specifically to keep mathematicians humble, which suggests either a cosmic sense of humor or that mathematical reality is stranger than we're equipped to understand. Well, my numerically bewildered number theorists, we've reached the end of another quantum calculation. Today we've learned that in the multiverse of mathematical discovery, every equation exists in a superposition of elegantly solvable and completely impossible, until a brilliant mathematician collapses the wave function into either a Nobel Prize or a nervous breakdown. We've discovered that mathematics is humanity's most ambitious attempt to make the universe make sense, despite the universe's apparent preference for keeping us guessing. From ancient Mesopotamians counting sheep to modern mathematicians wrestling with problems that might literally be impossible to solve, we've spent thousands of years developing increasingly sophisticated ways to be confused by numbers. Though I suspect somewhere in the quantum foam of reality, there's a universe where the Riemann hypothesis was solved by a Roman accountant using only an abacus and sheer determination. Want to explore more quantum corporate chaos? Visit us at multiverseemployeehandbook.com, where you'll find fascinating science news, deep dives into mathematical mysteries, and our latest blog series, Zero to Hero, a complete guide to numerical concepts your ancestors couldn't imagine. And if you've enjoyed today's numerical adventure, why not share it with a fellow mathematical mystic? Perhaps you know someone who still counts on their fingers, uses a calculator for basic addition, or believes that statistics are just opinions with decimal points. Spread our signal like the expansion of an infinite series. This is your quantum coherent correspondent, reminding you that in the multiverse of mathematical understanding, we're all just remarkably sophisticated arrangements of atoms trying to convince other arrangements of atoms that some arrangements of symbols represent absolute truth. And despite the fundamental incompleteness theorems, the unsolved millennium problems, and the lingering suspicion that zero might just be an elaborate practical joke played by Indian mathematicians on the rest of humanity, we continue to find mathematical beauty in the patterns that emerge from our cosmic confusion. Until next time, may your calculations balance, your theorems remain provable, and your encounters with mathematical paradoxes be limited to wondering why there are never enough coffee cups in the break room despite the fact that the number of employees remains constant. In mathematics, as in corporate life, some mysteries are destined to remain beautifully, frustratingly unsolved.
The Multiverse Employee Handbook was created by Rob Corrigan. The host, David, is a professional voice actor who has digitized his voice through 11 Labs voice cloning technology. All episode thumbnails are created with OpenAI, and music and sound effects come from Pixabay, which are generated by human artists. Everything else, the writing, jokes, research, sound editing, and coffee consumption, is 100% human-made by a human. No cats are harmed in the making of this podcast. Visit our website for more information about the Multiverse Employee Handbook.